and it splits into 1 and 2. So you can write down the junction rule, or, I mean, in this case, you can look at it and say, oh, that one has to be 3. And then if I consider the outside loop, like suppose I take a loop and I go on the outside, and I do the sum of the voltages is equal to 0, and I start here, and suppose I go, you know, this way. So when I go through this battery, it will be 20 volts plus 20, because I'm going in the same direction as the, well, I'm going from minus to plus. And then I keep going on the outside, and the current through this one is 3 amps. And since I'm going in the same direction as that current, it's minus 3 times 6. Keep going. When I go through this one, it's going to be minus 1 times R. And then I stop where I finished. So R has to be 20 minus 18, which is 2 ohms. And if I do this loop over here, let's say this is number 2, how about I call it the lower loop? And I go this way, right? That's me going that way. And suppose I start over here. So as I go from minus to plus, that's plus E. And then I'm going to be going in the same direction as that current, so it's minus 2 times 12. Go here. And then when I go in the same direction as this current to this resistor, it'll be minus 3 times 6. And then I stop where I started. So therefore E will be 24 plus 18. That makes it 42 volts. And that's it. You were asked to find the value of the resistance and the value of the EMF of that battery.
Do you know the answer for the orange one?
For the orange, I got, the buff color. The resistance, I got 10 ohms. And for the EMF, 28 volts.
Uh-oh. I don't know what it is.
So notice you didn't have to solve 2 equations to a known, 3 equations to the unknowns, right? You just look at the circuit. There are only 3 lines over here, or paths for currents. You got 3 amps here, got 1 amp over there. The 1 amp comes in here, and if you had 3 amps going that way, you must have had 2 amps coming in from this side. And if you had 3 amps going this way, and then 1 amp goes this way, then you gotta have 2 amps going this way. So either way you look at it, you gotta have 2 amps to the left in the midsection. Yes?
What is the answer, JB?
Oh.
The answer of 3B.
I just said it. It's 10 ohms for the resistance, and for the EMF, 28 volts. That's are those the numbers you got? Because I might have made a mistake too. I did it like that, then I
got 10 ohms, but I don't remember what my voltage was.
Yeah, so I got, it's in that circuit it was the same basic circuit. This is R. All I did was this, but it's the same thing. And this is E. And then I had 20 volts. Wait. I had 4 ohms over here. 32 volts over here. Put a resistor over here, 2 ohms. And then I said that the current here was 6 amps. And the current up here was 2 amps. Right? Well, what must be the current in the middle line or
4 amps.
segment? Can I have what?
4 amps
Which one?
to the left.
4 amps. Because if you have 6 and you get 2 going up, you must have had 4 going to the left. And if you have 4 coming in from this side, and plus this 2 is going to give you the 6 over here. So you know this 6 amps here, and that's what we have. So if I go on the outside loop, going this way, that's me going that way, and I start over here. So when I go through this, it's going to be plus 32. And then when I go through this resistor, it'll be, I'm going in the same direction as the current, so it'll be minus 2 times 6. And then I don't go across anything, keep going around, and then when I go through that one, it'll be minus 2 times R, and that equals 0. So 32 minus 12 equals 2R. So that's what, 20 equals 2R, so R is 10 ohms. And then if I consider the lower loop, and I go like that, and suppose I start over here. So when I go through this, from minus to plus, I'm increasing in potential, so that's plus that EMF, minus 4 times 4, minus 6 times 2, keep going, stop, that's 0. So this is going to be 16 plus 12, that makes it 28.
Oh, okay. I don't think I did too, I just misremembered it.
Because I remember 16 and 12. And I was like, yeah, my calculator, like 16 plus 12 equals, to make sure. Just gotta make sure to mess up the easy math.
I probably should have not binge 3 seasons of Attack on Titan.
So for the next exam, I'll try to pick
worth it,
things
it's
like
worth
this
it.
where you don't have to do all
Cultural
about this.
event.
You know, you see that then you can.
So are you in season 4 now?
Can I erase this now?
I should study.
Yeah, you can erase it. So you're in season 4?
I'm getting to the end of season 3 now.
Oh, okay.
I was thinking like an algebra mistake.
I know it's not assigned seats, but I feel super betrayed that someone stole it.
Oh, is that what you said here?
I looked over, I'm like, there's no empty seat there.
I always feel that way when I feel that way for other people too, because I'm like, it
This
feels weird when
circuit
when I see somebody else
is the
feel
circuit
like
in one of the
Michael's seat
problems
behind
in
me
the
or something. I'm
textbook,
like, what are you doing here?
for which I wrote down
Even though it
solutions,
doesn't
except
matter.
that I just changed the drawing a little bit. This circuit, and I changed numbers too.
Did you pass? Did you pass?
That's this problem.
Did you pass?
I mean, what's the difference between that circuit and this circuit over here?
We just got rid of one of the corners.
All I did was I moved that battery, I was able to slide it and I put it over here. That's all. I mean, that battery could be there, there, or there. It doesn't change anything. Right? Once you go through it, it'll be plus 28 volts or minus depending on which way you're going.
And you made it a triangle.
This resistor, I put it here and then the battery over there, but it's all on the same line, so you know it's the same thing. And then here you just have all on this line, you just have one resistor, right? All I did was I just made it look a little funny, boom, like that, but it's the same line, right? So this circuit is equivalent to that one. I just gave different, actually I see that I put the same 2 R's over there. Son of a gun, this looks like the same one. Oh no, there's a difference. Oh, this is 28 volts and I made this one 32. So the numbers come out different, so you wouldn't, just memorize an answer from the homework. But it's the same, this problem is the same as this one. You write a loop rule, you get an answer. You write a junction rule, you get an answer, and so on. You write the rules, and as you write them down, you get an answer, get an answer, get an answer, get an answer. But that circuit in that problem is identical to this. I mean, if I drew this circuit with the resistor here, for example, it wouldn't change anything. It's the same circuit. And all of this is just one path over here. I mean, I could draw it like this, like a semicircle if I wanted it, you know, and it's the same thing. So, that's that. So it turns out to be an easy problem if you practice applying Kirchhoff's laws and solve some of these problems, and then it's like, oh, you know, then it's an easy problem. If you haven't, and you're a little rusty, and should be plus, should be minus, then it takes you forever to solve the problem, and you're very likely to make a mistake, a sign mistake also, and that's when you run into trouble. So the one thing that I didn't say anything about yet, or actually I began talking about it, and I said I was gonna cover it today, is the R resistor connected in series with a capacitor.
Professor, before we get started, some of us are having trouble with the choral homework. Chapter 26, number 3, I think part C and G, none of us can get the answer to be correct.
4 amps and
0.0075 volts.
but yeah, try the same. Hopefully I'll put it there.
Which one?
3, C and G.
So this is the circuit right there? Maybe you're doing it correctly and they wrote down the answers incorrectly. Maybe. So it looks like you just have one loop over here, right? So you have 12 volts over here, and then a 10,000 ohm resistor, and then 20,000 ohms, and then 10,000, and then what? Another battery? 24. 10,000. There seems to be another one down there. And another 10,000. Wow, these people really like 10,000. Can you very quickly figure out the current? See, this battery is working against this one. This one wants to make current this way, right? While this one wants to make current this one. So which one is going to win?
The 24-volt battery.
This one. So overall, this voltage and this voltage together, it's like you just have a 12-volt battery. It's like you just have a 12-volt battery. And all of these resistors have the same current, so they're all in series. So let me start with this one. 10,000 plus 20,000 is 30,000, 40,000, 50,000, 60,000. So the current is going to be this way, and that will be 12 divided by 60,000. And that looks like 1 over 5, right? Well, maybe times 10 to the whatever. No, it's 5,000, right?
Yeah.
So that should be 10 to the minus 3 divided by a fifth. A fifth is 0.2. Wait, 1, 2, 3, yeah, times 10 to the minus 3. So this should be 0.2 milliamps. That's the current. But let's see, I haven't even read the question. So, yes, are we, but you know, let's say that didn't occur to you, right? And you said, oh, I'm gonna do a loop rule. Well, how do you do it then? Suppose you didn't do this. And you said, well, I don't know what the current is, but you know, this one wins over that one, so I will guess that the current is this way. Right? You know, the current is gonna be this way, it's gonna be this way, I is this way, I is that way, and that I is the current, not me. That's the current. This is plus, that's minus, that's plus, that's minus. So if I do a loop rule, and I go this way, and suppose I start here. I mean, I can start anywhere. If I go up, I'm gonna go from minus to plus, that'll be 24, right? And then, when I go in the same direction as this current, it'll be minus I times 10,000. And then when I go to this one, it'll be minus I times 20,000. And then when I go through this one, it's minus 10,000 I. And when I go through this battery, I'll be going down from plus to minus, so I'm dropping by 12 volts. And when I go through this one, it'll be minus I times 10,000 minus I 10,000, right? So minus 10,000 I minus 10,000 I equals 0. Well, the 24 and the minus 12 will give me 12, right? And then all of these are negative, right? I can bring them over to the other side, and I have 10,000 plus 20 is 30, 40, 50, 60,000 I, which is what I had over there, right? Yeah, this is correct, right?
Yes.
Okay, so you could also do it like that, but this one I would just look at the batteries. This one is working against this one, so it's like the overall voltage is just the difference between them, right? Because this one is going to win over that one by 12 volts. And then all of these, all of these resistors have the same current, so I can think of all of them as being connected in series. It's just the sum of all of them, right? That's how you combine resistors connected in series. That's just a shortcut, or you can always apply Kirchhoff's laws and get the same answer. So what is the first question?
I think it asks about resistance in R1. It asks in R1, R2. Like so.
The resistances are given.
Oh, I'm sorry. The voltage. Yeah.
Then it would be this times the resistances.
Yeah.
So for example, it may be an issue with how the answer is written.
I think that's what it is.
Yeah, it's 20,000 times 0.2. We're all getting 4.
So find the voltage across R1. R1 is this one, right? Oops, you don't see it. It's the one on the upper left. So the voltage across that one, so we have that the current is 0.2 milliamps or 0.2 times 10 to the minus 3 amps, right? But if you multiply that by 10,000, I can see that the answer is what? 2 volts?
Yeah. That was correct.
So the first question asks, find the voltage across R1. So this would be what? Is there a number here that, or you just type the
You
2,
did
right?
change it. Just type it.
And then here for units, do you write V?
Yeah. You have to press the X and then submit.
I have to press what?
The X and then submit.
This one?
Yep.
So that's correct.
Correct, and then that one's giving us trouble. We're all
Find
putting
the
in
voltage
4.
across R2.
Should be easy.
R2 is this one, right?
Yeah.
Mhm.
So that's times 20,000. So the voltage across, oh, R2 is the one up here, right? So the voltage across that one is I times R, right? So that would be 0.2 times 10 to the minus 3, and that's 20,000. Well, it should be twice as big as the other one, right? Is that therefore 4 volts?
Mhm.
Is that right?
Yep, it isn't accepting that answer.
Oh, then there's a mistake in it.
Watch it work.
I watched them updated it overnight.
Yeah, now that Dad's watching.
Okay, but that's supposed to be 4 volts.
And then G is also,
The voltage across R3.
it's
They're all
just two.
except for, C.
Yeah, because they all, yeah.
And then G is also messed up.
What we think.
So R3 is which one? The bottom one? Okay, so that should also be 4 volts, 2 volts, right?
Yeah.
So that one, it took it. R4 is also 2 volts, right?
They're all 2 volts except for R2,
Except for the last one.
for the 4 volt, yeah.
And then
It's the same.
F is R5, which is R5. Also, where is R5?
At the bottom.
Oh. And then what is the power supplied to the circuit? Well, the power supply to the circuit, see, this one is consuming energy because current is going into it. So it should be the current through this one times the 24. And so the power will be I times delta V. So I is 0.2 times 10 to the minus 3, and delta V is 24. So that is what, 4.8 times 10 to the minus 3?
Yep.
So it should be 4.8 milliwatts. Is that what you wrote down?
Oh, I did once.
So you write can you write 4,800? Or, I mean, I guess this thing has to allow you how to write down scientific notation, right? Does it take W for watts?
Yeah, I think so, from the other problems.
Did I do that right? Is the current times 24? That should be 2.4 times 2, should be 4.8, right? That's correct.
Did you use 12 or 24?
Well, this one puts out power, this one consumes, and this one is taking in that power because the current is into it. Remember the example that I did on the board the other day where the power we had like 2 batteries and then there were like 3 resistors, and then the power supplied by the stronger battery is the sum of the powers dissipated by the resistors plus the power that's actually taken in by this one because the current is into it.
But that's, milliwatts is a decimal, not 4,800. Right, it'd be 0.00.
So this would be 4.8 times 10 to the minus 3. Oh.
No, it wouldn't be
Thank you.
4,800.
Thank you.
I think I'm on the super
Right.
work because that one didn't mention that thing.
This should be
Oh, then,
0.0048, like that, right?
mhm.
Yes?
Yep.
Okay, so let's see.
Report for Greasman.
We go here. This is chapter 26, right? And that's, which problem is that? It's this one, right?
Yeah. An 8 volt. points. Okay, so they did the decimal.
Oh, no, am I off by?
No, they
No.
did it wrong.
They messed up.
No, I'm not off, right?
No.
No.
I mean,
You moved the decimal point over
or
and then
maybe.
two more zeros.
Yeah, I moved it, but then you got it, I mean,
That's correct. I think that's all.
cause,
No, you're.
yeah, I'm correct, if I use the calculator, so, then just forgot to put another zero here.
And
And
then
then the other one was 8 volts across R2. R2 is this one. No, but the current we said was 2, right?
Mhm.
2 times 4 is definitely, 2 times 2 is 4, right? So that should really be 4, not the 8 that they have. Okay,
Okay.
so this is problem number 3. Okay, I'll email them so they correct it.
Please give me
This could be a
Yeah.
solution. Minority, because what's- what else is-
How would that work?
Yeah, but the power supply is by this
You
one.
are the writer.
I think what I said the other day is that this one, since the current is coming in right into its positive terminal, then it's being charged. So it's not supplying it, it's actually taking in from the other battery. So this is converting it to thermal energy, converting to thermal energy, converting to thermal energy, converting to thermal energy, converting to thermal energy, but this one is converting it to chemical energy in the battery to charge it. So this battery is not supplying energy to the circuit. Okay, good? So, remind me at the end of class so I can send these people an email. Okay, so we wanted to consider this circuit. So this is the series RC. Circuit. Okay. So we have a, let me put the battery here instead. I mean, they put it like, actually, let me. Let me write it like this. Obviously, that's plus, that's minus. I will put the capacitor here. It's in series with the resistor here. All right. So the resistance here is R, capacitance is C, and the capacitor is initially uncharged. So the condition here is that the capacitor is initially uncharged. So if you like, there's a switch over here. I'm gonna call this a switch. And I can throw this way, right? So I can close the switch. So right now the switch is open. The switch is open. The charge in this capacitor is 0. Right? There's no current in the circuit because the switch is open. And as at t is equal to 0, so you close the switch. At t is equal to 0. So the condition is that at t is equal to 0, the charge in the capacitor is 0. It's called the initial condition. And as soon as you close the switch, at t is equal to 0, now we have a capacitor connected in series with the resistor. What can you tell me about the voltage across the capacitor and the voltage across the resistor? Since they are connected in series, what's the relationship between the voltages across two elements, circuit elements that are connected in series?
They have.
Yeah.
They add, right? So, and they have the voltage supplied by this battery here. So this is a, let's call it a DC battery. All right? So at t is equal to 0, remember that always the voltage across the capacitor is Q over C. Right? That's the master equation for capacitors, right? And the master equation for resistors is that the voltage across the resistor is I times R, Ohm's law, right? So at t is equal to 0, because the charge in the capacitor is 0, using this formula, if the charge is 0, then the voltage across the capacitor is 0 at t is equal to 0. Well, but if this voltage plus this voltage is equal to this voltage, then at t is equal to 0, we must have that the voltage across the capacitor is just the voltage of the battery. Get it? Or no? No? Suppose this is, the way we're going to do it in the lab, let's make this 3 volts. Well, if the charge across the capacitor is 0, what's the voltage across the capacitor? 0. But then this voltage plus this must be 3 volts. So if this is 0, this has to be 3 volts, which is the voltage of the battery. Yes?
Yes.
Now, as time passes by, charge will begin to accumulate in the capacitor. So which way do we say is the current in this circuit? This is just one loop, right? So not complicated, just one loop. Still, there are complications, but which way would you say is the direction of the current in this circuit?
Clockwise.
Clockwise, right? And that would be the direction that the positive charges would move. So essentially, the current is clockwise. So the current through the, I'm going to use a different color here. The current through the battery is, I'm going to call it I, and then the current through the resistor, I'm going to call it I. Because, all of these are in series, so they all have the same current. Now, the charges do not move across the plates of the capacitor. It doesn't go from one plate to the other. There's vacuum in between. There's, a capacitor is 2 conductors separated by some dielectric material. Let's say it's vacuum in between. So the charges are not going to jump across the gap in the resistor. In the capacitor. But thinking of positive charges flowing in the clockwise direction is equivalent to saying that the negative charges, the free electrons, are going in the counterclockwise. So essentially what happens is this. There are free electrons here, well, all over the place, because they are, these are conducting wires, right? There are free electrons. And as soon as the switch is closed, these electrons over here are repelled by the negative terminal of the battery, right? This electron over here is attracted to the positive terminal of the battery, or said differently, as soon as the switch is closed, there is an electric field set up. The electric field is set up this way, by this positive terminal. The electric field will be this way. The electric field will be this way. The electric field would be this way. The electric field will be towards the negative terminal. But remember that the force on the charges that move, right? Well, the force on the charges is given by this, but the electrons, which are the ones that move, are negatively charged, so the force on them is in the opposite direction to the electric field. So what will happen is that this electron is going to be actually, it will experience a force that way. This electron will experience a force this way. This electron is going to experience a force this way, right? Or said differently, this electron is repelled by the negative plate, or the negative terminal of the battery. This electron is attracted by the positive terminal of the battery. This electron is repelled by the negative terminal of the battery. Either way, the flow of electrons is in the counterclockwise sense. Now, but the electrons do not go across this gap over here. So these electrons that go in the counterclockwise direction, they'll begin to accumulate over here. And what about that electron, right? That electron, what happens is that there are electrons on this plate, and they are pulled to the left. So as one electron leaves, is gonna leave an extra positive charge behind, right? Because the plate is initially neutral. If electrons leave, then the plate remains positively charged. So then this will become positive. And so there will be a potential difference at that instant. As soon as some charge begins to build up over here, you get plus Q here, and you get minus Q there. And as soon as the charges begin to accumulate, now there will be a voltage across this capacitor. Suppose that a little later, the voltage across the capacitor is 1 volt. And this is 3 volts. At that instant, when the voltage across the capacitor is 1 volt because of the charge that has accumulated in this conductor, what will be the voltage across the resistor at that same instant?
2 volts.
It's got to be 2 volts because this voltage plus this voltage has to equal this voltage, which I'm taking to be 3 volts. So this will be, initially this is 3 volts at t is equal to 0, and then it's going to be 2 volts. And as more time passes by, more electrons will accumulate to be here, and more, well, there will be an excess of positive charges on the other plate. So this charge increases. And as this charge increases, the voltage across the capacitor increases. So a little later, the voltage across the capacitor will increase to 2 volts. But they're connected in series. The voltage across this plus the voltage across that has to equal the 3 volts, which is the voltage of the battery. So when this voltage across this capacitor is 2 volts, at that instant, the voltage across the resistor has to be 1 volt. Notice that this is the voltage across the resistor. Notice that the voltage across the resistor is dropping. It went from 3 volts to 2 volts to 1 volt. Now, the resistance is fixed. That means that the current must be getting smaller. So the current is decreasing as charge accumulates in the capacitor. And as more charge accumulates in the capacitor, right, then the voltage across the capacitor will increase, and then at some point, the voltage across the capacitor will be 3 volts. But at that instant, if the voltage across the capacitor is 3 volts, and this is 3 volts, what must be the voltage across the resistor at that instant? 0. And that means the current is now 0. Because if the voltage across the resistor is 0, that means that there's no current through the resistor. Another way of looking at it is the following. As electrons accumulate on this plate, on this conducting plate of the capacitor, no more electrons are allowed. It's like this fills up, and then these electrons over here tell the ones that are coming in, stop. There's no room for you over here. And so, then there's no more flow of electrons in the circuit, and then the current goes to 0. So, there was a surge of electrons moving in the counterclockwise sense, and in the beginning, there were a lot of them moving, and then less, and then none of them are moving. So what we want to investigate is how the current I in the circuit changes with time. What is its time dependence? And the current is related to the charge in the capacitor. What is the expression for the charge as a function of time in the capacitor? And, here's like the description. I didn't want to type all of this up in my notes or do the math. I'll just do it on the board. I think I just wrote down the graphs. I just didn't want to type all of that. Okay, so how do we find I as a function of time? So let's consider a loop rule, okay, at time t. T is equal to 0 is when you close the switch. So the sum of the voltages is, how about I go, this is me, clockwise. And I start over here. I'm going to start. All right, and I'm going to go clockwise. So as I go up, what will be the voltage across this battery?
E.
the EMF of it, right? And I continue. When I go across the capacitor, I will be going from the positive terminal or from the positively charged plate to the negatively charged plate, so I'm dropping in potential. Another way to look at that is to say this plus and this minus will generate an electric field this way, and if you move in the same direction as the electric field, the potential drops. So I'm going to drop in potential. But what is the voltage across the capacitor? What will be that drop?
Q over C.
Q over C. At that instant, the charge is Q and the current is I. And then I keep going, and as I go through this resistor, I'm moving in the same direction as the current, so the voltage across the resistor, and since I'm going in the same direction as the current, is also a drop, and that will be I times R. And then I keep on going, and I finish my trip, so that equals 0. And it's just a Kirchhoff loop rule for this simple circuit. Are we okay? So, if I solve for, I'm going to bring this over to the other side, so I got R times I plus 1 over C times Q equals this. But, what is the relationship between the charge that accumulates in these plates of this capacitor and the current in the circuit? Well, the current, it's related to the rate at which the charge accumulates in the capacitor, so it's dq dt. So if I take this and I plug it in here, and this equation becomes R dq dt minus plus 1 over CQ equals that. And if I divide by R, I get dq dt plus 1 over RC Q equals E over R, correct? And the condition, this is the equation we're trying to solve for Q as a function of time. Once I solve for Q, the charge as a function of time, I differentiate it with respect to time, and I'll know what the current is. And the condition, the initial condition is that Q is equal to 0 at T is equal to 0. So how do I solve that equation? So here's how I am going to solve it. So I have dq over dt. I'm going to write it as E over R minus 1 over RC Q. By the way, what must be the units of R multiplied by C? If I multiply this capacitance by this resistance, I'm going to get something in what units? It will be ohms multiplied by farads. But what must those units be also equal to? Look at this equation.
Volts divided by ohms. So amps?
Huh?
Amps?
Mm-hmm. Amps? No, amps is the whole thing. It's Q over RC. Q over RC is amps. The QDT is amps. Q over RC is amps. E over R is amps. I just want to know the units of RC.
Oh.
Not because if it's one or. Mm-mm. So, what are the units of this? Coulombs. And what are the units of this?
Coulombs?
And what are the units of this? Seconds. So what must be the units of this? Seconds. So R times C is a time interval. No? You don't see that? Right? I mean, I have dq dt. That's a charge divided by seconds, right? Plus Q over RC. Well, this is a charge. This has to be seconds. I cannot add something with 1 unit to something with different units. It's like this is equivalent to saying that I can add I cannot add a velocity vector to an acceleration vector. They have different units. I cannot add a velocity vector to a force vector. That's why we say in chapter 1 that when you add or subtract vectors, they must have the same units. Well, if this quantity is added to that to give me that, they all must have the same units. I mean, this quantity must have the same units as this, and it must have the same units as that. But because I know that this is charge, and this is charge, and this is time, then RC must be a time. It must be in seconds. That's just, something to know from just looking at the dimensions of the equation, right? But anyway, that was just a side question there. So RC is in ohms, farads, but that's equivalent to seconds. So that's what I have, right? What if I want the same denominator here, so what if I do this? Is that right? Did I do that right? Yes? And then what if I cross multiply? So then I'm gonna have dq over EC, which is a constant, right? It's whatever the voltage is of this battery, multiplied by whatever the capacitance of the capacitor is. Q is a variable. Yes? Agree with me? So notice that I have something that depends on time on the right hand side, something that the variable on the left hand side is charge, right? So now what if I integrate both sides of this equation? So then I do this, dq over EC minus Q equals dt over RC integral. Now the integral on the right hand side is an integral with respect to what variable? On the right hand side?
Time.
Time. So this is going to be from t is equal to something to t equals something. And what is our beginning? T is equal to 0 when the switch is closed. So I'll just integrate this from t equals 0 to some later time t. What is the integral on the left hand side of this equation with respect to?
0 to Q. Or wait.
But what am I integrating with respect
charge.
to?
Charge.
Charge. So my limits of integration must be values of charge, right? And I have to match this limit, this lower limit with this other lower limit. They're not the same, but if this is t is equal to 0, this would be the charge at t is equal to 0, which is? We started with 0 charge, right? And then this is the charge at time t. By the way, RC is a constant, right? So the integral on the right hand side, this is just one of the RC integral from 0 to t dt, which is what? All of that is just, on the right hand side is going to be equal to what? T over RC, correct? So all I need to do is this integral on the left hand side. What is that about integral? On the left hand side, what if I let u be defined as this constant minus q? And I say, what is the u dq? Because this integral is with respect to q, right? What is the derivative of u with respect to q?
-1?
-1, right? So that means that dq equals minus du. So then this integral becomes the integral of dq, which is minus du, over ec minus q, which is u. And on the right hand side I have t over rc. I haven't done the integral yet. All I did was a change of variable so that I can then recognize the integral on the left as something that I know what the value of that integral is. So I'm gonna write this as du over u equals minus t over rc. I'll just move the minus sign over to the other side. Now, you should look at the integral of the u over u and recognize that as
Natural log of
the natural log of U, right? So that would be the natural log of U, where U is this quantity, right? EC, which is a constant, minus Q, evaluated from Q equals 0 to Q, it's minus 1 over RC. Have I made a mistake?
No.
So, let me continue. Is it okay if I continue here? Or did I make a mistake?
What do we do to the T at the very bottom, 1 over RC? Are we saying that the,
No, this is one of those T's that's missing this one. It's an invisible line across. Thank you. Okay? So can I use this side of the board now? I mean this piece over here? Or do you want me to erase this? They're over there, so I'll just erase this then. So that will be the natural log of EC minus Q minus the natural log of EC minus 0, right? When I evaluate it like that, minus T over RC. Yes? And this is 0, right? And you know that the natural log of A minus the natural log of B is the natural log of A over B, right? So this becomes the natural log of EC minus Q over EC. Yes? And this is the natural log of 1 minus Q over EC and then how do you solve for the argument? You know that the natural log of A, if that equals B, right? This means that A is the base raised to the answer there, right? That's another rule. So this means that the argument here, 1 minus Q over EC equals E raised to the minus T over RC power. And then I bring this over to this side, and I bring that over to this side. And this becomes Q over EC equals 1 minus E to the minus T over RC. And then last step, Q equals EC, 1 minus E to the minus T over RC. And that's Q as a function of time. This is how the charge in the capacitor is building as time goes on, as time passes by. And if I want to know the current in the circuit, which is dq dt, we know how to take derivatives, right? So this will be equals 2. So EC times 1, that's a constant. The derivative of that with respect to time is 0. EC times this, it'll be minus EC times E to the minus T over RC. But by the chain rule, we need to multiply by the derivative of the power here, which is minus 1 over RC. So the C's cancel, and the minus sign cancels, and the current as a function of time is the voltage in the battery divided by the resistance times E to the minus T over RC. And notice, let's check, did I do that right? Or did I make a mistake? Well, suppose I consider t is equal to 0. So notice, at t is equal to 0, I know that the charge has to be, at t is equal to 0, the charge has to be 0, right? So if I use this formula, the charge at t is equal to 0 will be EC times 1 minus e to the minus 0. Well, e to the minus 0 is the same as 1 over e to the 0, which is e to the 0 is 1, 1 over 1 is 1. And 1 minus 1 is going to be 0, so q at t is equal to 0 equals 0. So I'm good. And it satisfies my initial condition. And after a long time, let's say t is equal to infinity, then q at t is equal to infinity, right, will become what? EC times 1 minus e to the minus infinity over RC. But e to the minus infinity is 1 over e to the infinity, which is 1 over infinity, which is 0. So this guy drops out. So after a long time, the final charge is going to be EC. In other words, it should be that, because when the voltage in the resistor goes to 0, the current will be 0. And if the current is 0, then, there's no voltage across the resistor. That means that this voltage must appear only across the capacitor, because there's no voltage appearing through this one, because there's no current. So the voltage across the capacitor will be E, but by this equation, by this one, you get E equals Q over C. So Q equals, this will be the final charge, it will be EC. Right? This will be like the final charge.
Crazy.
And that's what I have over here. After a long time, this will be like the final charge. Sometimes you say Q final is EC. And what about the current? At t is equal to 0, the current is what? E over R times e to the minus 0. So this is just E over R. See, at t is equal to 0, there is no charge in the capacitor, so there is no voltage across the capacitor. All the initial voltage appears across the resistor. And by Ohm's law, the current should be the voltage across the resistor, which is just the voltage in the battery, E divided by R. And that's what I have over here. I'm certain that I did this correctly. Right? It satisfies all of those conditions, everything that I expect. So the current, as a function of time, is given by this. Now, question. What is the voltage in the resistor as a function of time? Can I erase this?
Yes.
So what is the voltage at time t? Well, the voltage across the resistor will be given by what? I times R, right? But then I, the current, is given by this. So the voltage across the resistor as a function of time will be, well, it'll be this times R, which will be E times e to the minus t over RC. So let's, well, I can stop here with this discussion. And what we're going to do in the lab, is this. I will give you a resistor, and you're gonna set it, it's a decade box, where you turn some dials and you set it up to whatever value you want it to be. So I'll tell you to set it to 2000 ohms. I'll give you a capacitor, and it's one of those decade boxes, and then we're going to set this to 1 microfarad. So that's 10 to the minus 6 farads. This would be 2 times 10 to the 3 ohms. Now, what is the time constant of this circuit? The time constant is R times C, and that will be 2 times 10 to the 3 ohms multiplied by 10 to the minus 6 farads. And this will be 2 times 10 to the minus 3, but ohms times farads must be a time interval. So that's seconds. In other words, this will be 2 milliseconds. The time constant of the circuit will be 2 milliseconds. So, in the lab, we're going to use specifically these values. And we are going to set this to 3 volts. What I'm going to do is I'm going to give you a function generator, and we're going to set it to a square wave. So the voltage will be like this. So what we want is we want this to be t is equal to 0. And this is the voltage put up by the function generator. And we want this to be 3 volts. So it'll maintain the 3 volts for this time interval. At which point it's going to drop to 0. And then it'll be 0, and then it's going to go back to 3 volts. Then stay there, 0, then 3 volts. So what we're going to do is we want to play with the frequency of the function generator so that this time interval over here, before it drops to 0, this time interval over here is long enough for the capacitor to charge. And then we are going to use the oscilloscope, and we're going to use channel 1. And we have those, connector to channel 1, and we're going to use one of those cables, which is a coaxial cable that then splits it to a red and a black cable. And we're going to put the red cable here, red connector, and the black connector here. And we're going to monitor the voltage across the resistor on the oscilloscope screen. So during this time interval, we'll monitor the voltage across the resistor on the screen of the oscilloscope. And you'll see, I'm going to erase this. We'll set the oscilloscope screen to 1 millisecond per division. In the time base, you set it to 1 millisecond per division. You set this guy to you're gonna set it to 500 millivolts per division, which is 0.5 volts per division. Okay? And you know that this guy looks like, the screen on the oscilloscope looks like, so you have what? 1, 2, 3. The fourth one is the one in the middle, I think. And then 1, 2, 3, and I'm gonna call the fourth one. No. And then you have, I think you have 10 of these. 1, 2, 3, 4, I think you have 8 up, vertically, but you have 10 horizontal. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. All right, and the t is equal to 0. I'm going to ask you to set it right here. That way we can see what's going on below and to the left. Before, right? So that'll be like our origin. So then this is going to be, you know that on the oscilloscope, what do we plot horizontally on that axis, horizontally?
Time.
Time, correct. So this will be time in milliseconds. And this will be voltage, and actually the voltage across the resistor in volts. But each division is half a volt. So we're gonna set this to 0 here. So then this one here will be 0.5. In fact, I'm gonna put it right here. 0.5, this will be 1, this will be 1.5, this will be 2, this will be 2.5, and this will be 3. That way, we can fit the 3 volts, in as much of the screen as we can. And we can see, before the capacitor begins to be charged and, negative voltages too. So, this is what I just did on the board, right? We predict from theory, using Kirchhoff's laws, doing an integral, we predict that the voltage across the resistor is going to be this. Right? So, we're going to erase this. This will be the easiest lab, believe it or not. So, by the way, this in milliseconds, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 milliseconds, right? Because each division is 1 millisecond, right? And this is 0. So I want 0 to start right here, right? So the voltage across the resistor that we are going to monitor is E times e to the minus t of RC, right? So this will be 3 volts times e to the minus t over 2 milliseconds. Because RC is 2 milliseconds, right? That's the voltage across the resistor as a function of time in volts. So, what if the time in milliseconds is that, and this is the voltage across the resistor in volts? So, if t is equal to 0, what's the voltage across the resistor? If that's 0, 0 divided by that is 0. E to the 0 is 1, so that should be 3. That should be this point right here. How about 1 millisecond later? Well, 1 millisecond later, I'm going to erase this. So this is 3 volts e to the minus t over r over 2 milliseconds. Well, if t is 1 millisecond, then the voltage across the resistor will be 3 times e to the minus 1 millisecond divided by 2 milliseconds. The milliseconds cancel. This is 3 times e to the minus 0.5. So use your calculator. How much is e to the minus 0.5? And then multiply by 3. 1.8? All right, so, someone else check, just in case. All right, so 1.8 should be 1 millisecond, 1.8 should be around here,
About 1 millisecond.
less than 2,
At 1 millisecond, right?
what's that?
You put it at 2 milliseconds instead of 4.
Oh, I did 2 milliseconds, thank you. So, like right there. Good. And then, I want you to do this. What if it's 2 milliseconds? Then, at 2 milliseconds, you're gonna have 2 milliseconds divided by 2 milliseconds, this is e to the minus 1. This is 3 times divided by e. How much is that?
1.1.
1.1? 1.15 or something like that? So 1.1 would be like around here. Okay, I mean 1.2, 1.3, 1.4, 1.5. So around there. And then I want you to do this with your calculator at 1 millisecond, 3 milliseconds later, 4 milliseconds later, 5 milliseconds later, 6 milliseconds later, 7 milliseconds later, right? So you put in the different points over here, right? So, these dots are coming from this table, and these values were calculated using this formula that we obtained using Kirchhoff's laws, right? This is theory. Now, on the oscilloscope, you're going to be measuring directly, experimentally, the voltage, monitoring the voltage across the resistor. And what I want you to do then is you can take a picture of it, right? Or you can draw it, and you'll notice that when you draw the curve that you will see on the oscilloscope screen, right? The curve is pretty much going to do this. It's gonna go, it's gonna go like this, it's gonna go like that. So this decay over here with time is gonna be exponential, and I want you to label the curve, and I want you to put the points from the theory on the same graph so that we can see how close the data values are that we predicted from theory to what you actually see on the screen of the oscilloscope. And you'll see it's like very, very, very close. So essentially we're going to use the lab to test, to verify this expression, to see if it's really good. And you may be off a little bit because, these resistors, you're going to set this box to 2,000 ohms, but it may be 2,002 ohms, it may be 1,997 ohms, it'll depend on the box that you get and so on. So there might be slight differences, but you'll see that we're going to get a very, very good agreement in general. So all you'll do is you'll come in, you can do this at home before you come in, then you'll know what these values are. It'll be just a matter of plugging on the circuit, boom, taking a picture, and that's it. You're done with that lab as far as taking data. Then you just, on the same graph, you can put the dots for the, from theory, on the same graph that you get experimentally, right? And so, anyway, that's what that lab is going to be about. It'll be very quick. You just connect it, watch it, observe it, and that's it. And then I ask a couple of questions, and anyway, that'll be that particular lab. Although before we did that lab, I kind of wanted to do a lab on Ohm's law, so that's what I wanted to do this week. So while you can go through this calculation yourself if you like, Anyway, I kind of wanted to go in detail through this calculation because the more detail I go into it here in class, the easier the lab is going to be. Otherwise, then the lab is, it's like, oh. Can I erase all of this? So this is what we're going to be considering. So, it's, I think, very useful to think of this circuit from a conceptual point of view. Like this capacitor is connected in series to this resistor. And the sum of those two voltages must be equal to the voltage supplied by this, right? Which is fixed at 3 volts. So this voltage plus this voltage was equal to that. And in the beginning, there's no charge in the capacitor, so there's none of the voltage of the 3 volts over here from the pattern will appear across the capacitor. So all the 3 volts are going to appear across this. That's when you have the maximum current through the circuit. After that, the capacitor charges, the current dies out, because, these charges that accumulate over here won't let any more charges come into it, and then the current is going to go to 0. This is the voltage across the resistor. Well, notice that as the capacitor charges, the current goes to 0. If the current goes to 0, the voltage across the resistor goes to 0, because the voltage across the resistor is I times R. So if the current goes to 0, the voltage across the resistor goes to 0. Which means that as that's happening, the voltage across the capacitor is getting closer and closer to 3. When the current dies out completely, that's when the capacitor is fully charged. All of the 3 volts will appear across the capacitor. Now that'll be charged. So it's important, I think, in order to get more out of this, to understand the concept. And then you can do the details of the math of the integral. How do you solve that equation and do that integral, and there's a natural log involved over there, and put in limits, and then you do that part. Okay. So with this, we finish this chapter. And the next chapter, I'll just say a few words that I want to cover is actually 28, not 27, but 28. So, I'll do this in more detail next time. In chapter 28 and 27, we talk about magnetism. So, we talk about magnetic fields. Just like we talked about electric fields at the beginning of the course, now we'll be talking about magnetic fields. And magnetic fields are vector quantities. Just like electric fields are vector quantities, just like gravitational fields are vector quantities. So they have directions associated with them, right? They're vector quantities, they have direction associated with them. The unit of magnetic field in the metric system is anyone? No? Tesla, correct. After Nikola Tesla. So what is his last name? So the unit of magnetic field in the metric system is the Tesla. There are other units of magnetic fields. The Gauss, which is somebody else's last name, is also a unit of magnetic field, but it is not in the metric system. So we want to talk about magnetic fields and be able to calculate magnetic fields. But you'll see that these two chapters, so, starting over here, has cross products in it. See? There's a cross product right there. And we need to be able to evaluate, do a cross product. Cross product right there. And then blah, blah, blah. Those are results of cross products, blah, blah, blah. Here, no cross product. Okay. Not much, apparently. When we go to the next chapter, which is when we learn about what magnetic fields are good for, in chapter 28, we learn to calculate magnetic fields, and we need to know about cross products. But then in chapter 27, now we ask, well, what will magnetic fields do to other things? Well, this is a force, a magnetic force. Notice there's a cross product in there. This is the force that a magnetic field will exert on a point charge Q moving with velocity V in an external magnetic field B. And you have to do the cross product, multiply by the charge, get the force on it. So there's a cross product in it. What if you put a wire with current in it, in this external magnetic field? What will be the force that the magnetic field will exert on the wire? Well, it'll be this, and there's a cross product in it. What if you take a loop, maybe a coil with many turns, maybe just one turn, with current in it, and you place it in some region where there is a magnetic field? What will the magnetic field do to the loop? Well, it'll exert a torque on it. And how do you calculate the torque that the magnetic field exerts on the loop? And if there's a torque, it'll make it spin. Right? So, well, how do you calculate the torque? There's a cross product in it. You get the point. The point is, we need to know about cross products so that we can appropriately apply it in here. And then we can also talk about magnetic energy, but energy is a scalar quantity. So how do you get scalar quantities from vectors? Well, when we calculate magnetic energy, there's a dot product in it. So dot product. Can't afford to forget that product either. And depending on the orientation of the loop with current in it, the energy could be a minimum, it could be a maximum. Right? You want to analyze the motion of a charged particle, for example, in an external magnetic field. Well, we'll have to use the cross product, and if the force is perpendicular to the direction that the particle moves, then it will move in a circular path. And remember centripetal acceleration and centripetal forces. Okay, so we're going to apply that. Aurora Borealis, applications. This one here is an interesting application. You have a charged particle coming in here, and in this region of space, there are this set of parallel plates. There's a positively charged plate over here, and a negatively charged plate over there. So it's like you have two plates like this. This one is positively charged, right, the one on the right, and this one is negatively charged. So they generate an electric field. Those plates that are charged, pointing which way is the electric field that they generate? This way, right? And the particle is coming in this way. And, but you see these dots over here? These dots represent a magnetic field that's also in there coming out of the page, out of the board in this picture. So dots are used to represent, like, the vector is coming out towards you. X's represent vectors that go into the page. So this charged particle, this positively charged particle, is going to come in here, and it will be exposed to an electric field generated by the charges on these two plates, which is the electric field is this way. And on top of that, in addition to that, it will be exposed to a magnetic field. And both of them are going to exert forces on the charged particles. And through the cross product, we'll see that the forces will be in opposite directions. And if you adjust the charges here, the voltage here, and so on, you can make those two forces, the electrical force and the magnetic force, cancel out, and the charged particle is just going to go straight if it has the right speed. So that's called a velocity selector. And then, if it has the right speed, it's going to make it through this hole, and when the charged particles go into this region over here, there's no electric field over here, only the magnetic field, and the magnetic field is going to make it go in a circular path, and then you can measure the radius. You see where it hits over here, so you know what the diameter is. Half of that is the radius, and then you can, make measurements as to what the charge of the particle is, what the mass of the particle is. You can do spectroscopy with this. The point is that it's kind of more interesting because now we begin to see something about applications. But I begin chapter 28 with a discussion of cross products, because you cannot successfully solve problems in this topic of magnetism if you don't know about cross products. So what I'll do next time on Wednesday, right, is we'll discuss cross products. I'll remind you how to calculate cross products in case we talked about it in the first chapter of Physics 185. We'll need to know the cross products between the unit vectors. What is I cross I? What is I cross J? I cross K? J cross I? J cross K? J cross J? What is K cross I? We're going to do all of that, and then once we review the cross product of vectors on Wednesday, maybe half an hour or something like that, then we're going to go deep into magnetism, because those formulas are just a lot of them contain cross products, and we need to know how to apply those. Okay, so that's the plan. All right, have a nice day. I'll see some of you later today, about an hour and a half.
Just about to say that the class now.